Example 3.1.8, a 50 Hz Y-connected 6-pole synchronous generator has a synchronous reactance of 1 ohm per phase with negligible armature resistance. Its full load current is rated to 60 amps at 0.8 power factor lagging, and the field current of the generator has been adjusted such that the no-load output voltage is 480 volts. Draw the phasor diagram and find the magnitude of the output voltage for the generator operating at rated current. So the givens here are that we have let's see, 50 hertz. F is equal to 50 hertz. It's Y connected. There are 6 poles, so P equals 6. The magnitude of the armature current is 60 amps. The power factor is 0.8 lagging. And V line to line under no load conditions is equal to 480 volts. We're asked to draw a phasor diagram. And we're asked to find the magnitude of the output voltage, which is a line-to-line voltage, under rated conditions. Okay, so the solution to this, I'm going to start with kind of an explanation of what's going on here. It's sometimes a little confusing. Remember that the generator has 2 parts. It's got the spinning part called the rotor, and it's got the stationary part called the armature. And the rotor circuit looks like this. I've got a DC supply and what's called the field coil, and I've got a DC current flowing through that called the field current. What happens is that produces a magnetic field in this coil that induces an AC voltage in the generator. A lot of times this is called the excitation field or the excitation voltage. It's given the symbol EF. So this thing spinning induces an EF over here. The size of EF is dependent on 2 things: how much current is flowing through this electromagnet, and that's because more current produces a big magnetic field. And then the second thing is dependent on is how fast this whole thing is spinning. We don't typically alter how fast it's spinning because the rate that this thing spins at sets the frequency of the AC source. So that's not a good way to control the size of EF. A better way is to just change this field current, increase the size of this magnetic field, and get bigger EFs. So that's the mechanism by which the magnitude of EF is typically controlled, is with this adjustments made to the field current in the rotor circuit. So that's the effect there. And so whenever a question says the field current of the generator has been adjusted such that, what they're saying is that they've adjusted this here to produce a known quantity of voltage in the armature circuit here. So that's part 1 of the explanation. Part 2 is that there's a circuit model for the armature. That is that it has a synchronous reactance X sub S associated with it, and it has an armature resistance R sub A associated with it. So the voltage here that I'm indicating is often called the terminal voltage of the generator, and this is the phase version of what's actually measurable at the output terminals of a generator. So you actually really can't measure this internally to a generator because of these. So there's that explanation. So from the givens, we were told that the field current of the generator here had been adjusted such that the no load output voltage is 480 volts. Well, what that's saying here is that if I measure this without any current flow here, this voltage and this voltage have to be the same because there's no voltage drop across these elements if the armature current is 0. So if that current doesn't exist, the voltage here has to be equal to the voltage here because there's no current flow and therefore no voltage drop across the internal coil. So we call that a lot of times the no load condition. So it was specified as 480 volts. Remember, that is going to be a line-to-line quantity. So we'll say VT no load is equal to 480 over root 3. So that's going to be equal to 277 volts. Since there's no current, that means EF is going to be equal to 277 volts. So we were able to determine EF by measuring VT under a no load condition. And I should say that's the magnitude of EF is 277 volts. Okay, so we've got that. The question was draw the phasor diagram for this circuit when it's operating at rated current. So now what's happening is we're delivering power to a load, and that load is drawing an armature current IA that's going to be equal to 60 amps at a power factor of 0.8, which is negative 36.87 degrees. So what happens to the terminal voltage when this much current is drawn? EF can't change because that's fixed by the field current, so the terminal voltage has to change because of the voltage drop across these elements right here. So in this example, XS was 1 ohm. It's an inductor though, so it's J1, and RA was equal to 0. So if I want to draw the phasor diagram for this, in generator analysis it's very common to take VT as the reference phasor. So we draw VT here, and we've got a current that is at 60 angle negative 36.87. So that's 60 degrees, and this angle here is negative 36.87. There's going to be a voltage drop here that is equal to J1 times the current. So this voltage drop, because of that J, is going to be 90 degrees out of phase with that current. So if this is the current vector here, that voltage across this element right here is going to be 90 degrees out of phase with it, right? And so that vector right there is going to be 60 at angle negative 36.87 times J1, which is going to be equal to 60 volts at angle 53.13 degrees. And if I connect those two, that's VT right here, plus the voltage drop across this element has to equal EF. So that's the phasor diagram. I'll indicate that that angle between the excitation voltage and the terminal voltage is often called the power angle, given the symbol delta right there. So there's the phasor diagram. What we're asked to do now is to determine the magnitude of the output voltage here. So first step in doing that is to determine what VT is. And so I can just say that I don't know the power angle delta here. It changes as load changes. EF stays fixed. I know that that is equal to 277. That can't change under load. And then I know the magnitude of this phasor right here. So to solve this problem, I have to apply a little bit of geometry. I have to take this phasor and project it onto the X and the Y. And the reason I do that, I'm going to get another pen here. The reason I'm doing that is that I want to solve this right triangle that I just drew in red. And if I do that, if I solve for that right triangle, I can determine what VT is by dividing the base of this right triangle into VT and then the projection of this vector onto the x-axis. So I'm going to write that as an equation. Go back to my black pen first though. That would be using Pythagorean's theorem. The hypotenuse here, 277 squared, is going to be equal to the base squared. So that's VT plus the projection of this vector onto the x-axis. So this is going to be plus 60 cosine of 53.13. So those added together are the base. I need to square that because it's Pythagorean's theorem, and then I need the height of the triangle here, and that's going to be 60 times the sine of 53.13 degrees squared. So I need to solve that equation. That'll give me VT. So 277 squared minus this squared, take the square root of it, and then subtract off 60 cosine of 53.13. You'll find out that your terminal voltage is 236.8 volts. Don't take my word for it though. Make sure that you do that calculation yourself so that you're manipulating that equation appropriately. I also want to warn you that this is not always the case. I developed this equation based on this phasor diagram. The equations are different if you have a leading power factor or if you have a power factor of 1. So this isn't a catch-all equation right here. This only applies to leading power factors. And additionally, it only applies if RA is equal to 0. So we've done some major simplifications right there. Anyway, that gave us the terminal voltage, but we were asked to determine the output of the voltage or output of the generator, and so we know that the magnitude of the line-to-line voltage is going to be equal to root 3 times the magnitude of the terminal voltage. I guess that should be magnitude. So that's going to be root 3 times 236.8, and that's going to give me 410.15 volts. So under load, this generator right here is going to have a line-to-line output voltage of 410.15.